Every single day, thousands of bursts of radio energy are detonating across the universe, each one lasting less than a millisecond, each one releasing more energy than the sun produces in 3 days. They come from every direction. They come from billions of light years away. Most of them fire exactly once and never repeat, which means we almost always miss them entirely. We have been detecting them since 2007. We have found hundreds of distinct sources. We have built entire new telescopes specifically to catch them, and we still do not know what makes them. The universe has been screaming at us for at least 17 years, and we cannot identify the voice. Before 2007, the working assumption in radio astronomy was straightforward. Any bright, sharp radio pulse you detected came from something inside or very near our own galaxy. Pulsars, rapidly spinning neutron stars, had been producing detectable pulses since 1967, and they were well understood. If you saw a radio spike, you looked for a known pulsar. That was the mental model. It was a reasonable model. It held for 40 years. Then Duncan Lorimer and his student David Narkevic were going through archived data from the Parkes Observatory in Australia, data that had been sitting on hard drives since 2001, and they found something that did not fit. A single pulse, lasting 5 milliseconds, so bright it saturated the detector. But the dispersion measure, the way lower frequency radio waves lagged behind higher frequency ones after traveling through ionized gas, was off the charts. It implied the signal had traveled through an amount of intergalactic medium consistent with a source billions of light years away. Not a local pulsar, not even close. Actually, here is something almost nobody mentions when they tell this story. The Lorimer burst, as it became known, was discovered in archival data 6 years after the telescope actually recorded it. It had been sitting there, unnoticed, since 2001. We had already detected a fast radio burst before anyone knew fast radio bursts were a thing. Anyway, the energy implied by that distance was staggering. To be that bright from that far away, the source had to release, in 5 milliseconds, the equivalent of the sun's total energy output across 3 full days. One object, one event, 5 milliseconds. The next segment will cover something that made the entire field more complicated. Some of these bursts repeat, and the ones that repeat do not behave the way any single known object should. The standard picture after the Lorimer burst was that fast radio bursts were cataclysmic one-time events. Something destroyed, something collapsed, something that could only happen once per object. A neutron star merger maybe, a collapsing magnetar, a death event. That picture made sense because every burst found in the first decade fired once and vanished. Then in 2016, the Arecibo Observatory detected FRB 121,102 firing again, and again, and again. The same source, repeating. That broke the cataclysmic model immediately because whatever was producing these bursts was surviving them. The Chime Telescope in British Columbia, a radio telescope that looks like 4 side-by-side ski halfpipes and has no moving parts, began operations in 2018 and immediately changed the scale of this field. It detects the sky continuously across a wide band. Within its first year, it had found dozens of new fast radio bursts, including several more repeaters. It demonstrated that the rate of fast radio bursts across the whole sky is roughly in the thousands per day, not per year. Per day, 1,000 fast radio bursts every day reaching Earth. The repeaters and the non-repeaters do not look the same. Repeating bursts tend to be wider and more complex in structure. Non-repeating bursts are typically shorter and sharper. This suggests they might not share a single mechanism. The universe might be producing fast radio bursts through at least 2 different processes, which is either a clue or a headache depending on your perspective. By the way, in 2020, a fast radio burst was detected from inside our own galaxy, from a known magnetar called SGR 1935 plus 2154. It was 1,000,000 times fainter than extragalactic FRBs, but it confirmed magnetars can produce them. Whether they explain all FRBs is still an open fight. What comes next is where it gets genuinely strange, because astronomers have found a way to use these bursts to measure something about the universe itself that no other tool can reach. Here is the thing about the dispersion measure that makes fast radio bursts more than just a mystery to solve. It makes them a tool. When a fast radio burst travels across billions of light years of intergalactic space, it passes through the diffuse plasma, free electrons, that fill the voids between galaxies. Lower frequency radio waves interact more with those electrons and arrive slightly later than higher frequency waves. The size of that delay, the dispersion measure, tells you how much ionized matter the signal passed through. And if you know the distance to the source independently, you can calculate the density of matter along that line of sight. This matters because of something called the missing baryon problem. Models of cosmic structure predict a certain amount of ordinary matter in the universe: protons, neutrons, electrons, the stuff that makes up stars and gas in you. But when astronomers add up all the matter they can actually see, they only find about half of what the models require. The rest is theorized to be spread through the intergalactic medium as a thin, nearly invisible warm gas, too diffuse to see in emission, too spread out to detect in absorption. It has been missing from the census for decades. By the way, the amount of matter missing from that census is not a small rounding error. The universe appears to be hiding roughly half of all the ordinary matter that should exist, in filaments of gas between galaxies that are so thin they produce almost no light at all. In 2020, a team using localized fast radio bursts with known host galaxies used the dispersion measure technique to directly measure that missing baryon density for the first time. The number came back consistent with predictions. The baryons were there, strung out in the cosmic web, invisible to every other instrument, readable only through the delay in a millisecond radio pulse from a source billions of light years away. Right now, multiple observatories are running programs specifically designed to localize hundreds more FRBs to their host galaxies. And one measurement expected within the next few years could answer a question about the universe's expansion that two different methods currently disagree on. CHIME is currently the most productive FRB detecting instrument on Earth, logging new bursts at a rate that was unimaginable a decade ago. The CHIME FRB collaboration is actively building outrigger stations, smaller copies of the telescope placed thousands of kilometers from the main array in British Columbia. When a burst arrives, the time delay between the outriggers and the main telescope gives a precise position in the sky, precise enough to identify the host galaxy, precise enough to start doing cosmology. The DSA-2000, a proposed 2,000 antenna array in Nevada, is in development with the explicit goal of localizing thousands of FRBs per year to their host galaxies. If it operates as designed, it will generate more FRB localizations in a single year than the entire field has produced in its history. The first results from that program could land within this decade. By the way, CHIME was not originally designed to find fast radio bursts at all. It was built to measure the large-scale structure of the universe using a technique called hydrogen intensity mapping. FRBs were a secondary science case. They became the primary result almost by accident. The Square Kilometre Array, currently under construction in South Africa and Australia, will have sensitivity that dwarfs anything operating today. SCA pathfinders like Meerkat in South Africa are already catching FRBs and probing their local environments in detail. If the magnetar model is correct, and the upcoming localizations confirm that repeating FRBs cluster in star-forming regions where young magnetars are most common, that closes the case for at least one class. If the localizations show something else, old galaxies, quiet environments, no correlation with stellar age, then the field is back to the beginning with much better data. Now return to the first thing you heard at the start of this video, because it means something different now than it did 90 seconds ago. Every single day, thousands of bursts of radio energy are detonating across the universe, each one lasting less than a millisecond, each one releasing more energy than the sun produces in 3 days. You now know what dispersion measure is and why it works. You know what Chime found and what the missing baryons were hiding in. You know that a galaxy-scale measurement came from a 5-millisecond scream across billions of light years. The bursts have not changed. What changed is that you can hear them now. Do you think we identify the mechanism behind non-repeating fast radio bursts before 2035? Yes or no? Follow Pancake's house. New video every week.